Hi guys, welcome to Learning Electronics Repair. This video started out as part of one of the car boot videos, the PC retro finds, but what I did find, although it wasn't retro, is this motherboard, and this motherboard has a short circuit. It's not of any great value at all as a motherboard itself, but this will be a very good example to use for short circuit tracing. Okay, so I'll just play now part of the original video. You'll see how I found this motherboard, you'll see what's wrong with it, how I've tested it so far, and how I've proven there's a short circuit. After that, let's get the pen and paper out. Let's just draw a bit of this so you understand how the circuit is working, where the short circuit might be, and then let's see if we can trace a short circuit on this motherboard. There are a variety of different ways we could do that. We may end up using more than one way, but we can also chat about the various methods as well. Okay, so first, this is the video I recorded when I found this motherboard. Yeah, it looks like a... Oh! This is not what I expected at all. So this is a socket 775 with PCIe. So this is not a retro machine. It looked like one, but it isn't. This I don't think will be worth anything. I'm buying a lot of these just, you know, how they look. I'm not getting really the chance to have a look at them properly because the guy is just finding me batches of machines. Okay, so a bit disappointing, this one. Here's the motherboard then. As I say, this is not really the sort of thing you should be buying if you're looking for retro PCs. It came in a job lot. It looked old. It's not so old. We should just check there are no short circuits on the 12 volts. And there aren't. That's fine. So you can actually see the analyzer under this screen there. I'll just set this to VGA. So I've put the graphics card that came with it. Just let's have a look. Okay, power on. In fact, no, power's on now. Does it start? Yeah, then it goes off. Oh, that's interesting. Okay. Again? Nothing. Well, I didn't see any short on the 12 volts. Okay. You can see it from that angle. There's definitely no short there. But interesting, that stopped. And it's like the power supply cut out as well. Is there any shorts down here on the, let's see. Well, the voltage supply, so 3.3, that's fine. The other 12 volts here, it's fine. 5 volts, fine. So there's no shorts there. Switch the power supply off at the mains. Switch it back on again. What does it do? Same thing. And then it won't start, I guess. I've took the graphics card out, take the RAM out. Once again. Well, you know, guys, I said I wasn't going to lose any sleep over this one. That suggests there's like some sort of problem with the chipset or something. I think we can just confirm this actually. So, if I still have standby, then the power supply hasn't effectively gone off. I don't think it has. Let's see. So volts DC, the violet one. Yeah, standby's still there. Okay, so if we go to the green one, that's now low. We'll switch the power off. Just wait for the standby to effectively go away. Look, something happened there, yeah? Can you see that? Switch it back on. Now this should go high, I would think. Yeah, 5 volts. Now when we hit the start, this should go ground and it should start. And it goes ground and stays grounded, okay? But it doesn't do anything. Is the power supply actually still on? No. So this is sort of like something's causing the power supply to go off, I think. It's a bit hard to say on this one. There's some voltage regulators on the board. Let's have a quick look. So I'm looking for shorts now again, okay? Just go into the continuity mode. So, well, that's probably ground anyway. What resistance is on here? No, 60 odd ohms. 60 odd ohms. This is probably ground. That's probably supplied to that chip. Another one up here. What we got? 12 ohms, probably supplied to this one, just a guess. Another one down in the corner here, this would be the RAM supply, you would think. No short on there. Some more here actually. What we got here? No, there's no short there either. Yeah, 42 ohms. That might be supplying that one actually. So it's more likely some sort of chipset thing. Switch the power on again. Let's check for shorts on the V core actually, just before I try it again. Maybe that is the problem. Okay. So V core, well, we've got, I'll show you, various VRMs down here. Okay. One side will be the 12 volts coming in. Here looks like it was what I was reading on the 12 volts then. Same. Those read very low. That could be ground or it could be the CPU. Let's look on these ones. I see some more. These look a bit more like I'd expect the layout to be. So that's the 12 volts coming in, I would say. Then this might be the junction between there and there. Let's just take the processor out. Now what do we see? Okay, so 12 volts coming in. That's gone higher now. We might have a short circuit CPU here actually. Possibly a shorted CPU, that's a bit unusual. But that's how it works. So again, that's on the 12 volts coming in. Then I'm just trying to find out which end of the MOSFET. There. And then you would expect the source of this and the drain of the other to be the junction that goes to there, yeah? To the coil. That reads low. That reads low. So we do have a short on that rail, but it's not the CPU. And it's not a short circuit high side MOSFET. This will be ground, I would think, over here. This could be an interesting one, just to diagnose the fault. Let's see if we can find where the short is. It could be if this chip is also connected to vehicle and this has a short in it. Could be a capacitor or something. I think this is a good one where we can inject some current and see what gets won. We know then we have a short circuit somewhere in this VRM or something that's being driven from the VRM. This is why it was important to remove the CPU to test that, because that is one of the components which is powered from this voltage rail. And these CPUs, even good ones, can read very low resistance, maybe just a few ohms or less. So you need to remove that just to prove you're not measuring the resistance of the CPU. Yeah, but we took that out and we still have the low resistance. The problem is now that we don't know where the short is, and this is not always straightforward to find out. Let me just put this onto paper for you and then explain how the circuit is working, then you'll have a good idea of what we need to do. And we will just notice, by the way, we have 1, 2, 3 coils here. Okay, let's draw this. The VRM, or voltage regulator module. I'll write that out, and while I'm doing that you can just remember it. Module, okay. So this is a type of DC to DC converter. On our motherboard it takes a 12 volt supply and it generates a low voltage that the CPU requires to run on. And in fact some other components on this motherboard will also run from that voltage rail. The output from the VRM will vary, and that's because on modern motherboards and graphics cards as well in particular, the GPU or CPU can actually request its own voltage. So when you first power up, it starts off at a certain preset voltage, and then the GPU or CPU can request more or less depending on the load at the time. So it effectively regulates its own supply. It asks for its own supply voltage. The VRM is made up of phases. So on ours we have 3 inductors, 3 coils. That means we have 3 phases. And each phase looks roughly like this. So we'll have a 12 volts input. Okay. We will have, I'll draw it like this, make it easier. We'll have the first phase, which is made up of a high side and low side MOSFET. Like so, and this goes to ground. This 12 volt supply will have lots of capacitors on it connecting to ground. So there'll be many capacitors. Okay. The 2 MOSFETs are switched by a pulse width modulator controller. PWM, let's put PWM1, PWM2. And the output connects to a coil. We can draw it this way around, doesn't really matter. Usually the MOSFETs are drawn the other way around, but that's just the way my piece of paper worked, okay? The inductor then connects to the load, in our case is a CPU, plus other things, okay? And on the output here, again, there are lots of capacitors connecting to ground. And that is basically one phase. Ours has 3 coils, so there are 2 more phases, so I'll just quickly draw that. So there is our 3-phase VRM. Now there's a few things we need to notice. One is that there may be more than one MOSFET in parallel. So this is the high side. And this is the low side, and they called that because this one connects to the high voltage, 12 volts, and this one connects to ground, the low voltage, okay? And it's not unusual to find we may have something like this. Two MOSFETs in parallel. This will then go to PWM2 there. Yes, there'll be some resistors in series with the gates, but that's the basic thing, yeah. And you can also have VRMs where there's more than one high side MOSFET in parallel, and also more than one low side in parallel. That sort of thing. This is just to share the load. If you have 2 MOSFETs in parallel or more, you can handle more current. These phases don't all switch on and off at the same time. They work alternately, maybe one at a time, or if you have 6 phases, you may get pairs at a time, something like that. Then it may just be 120 degrees at a phase, so effectively as one is powering up, the other one powers up a little bit later. It doesn't wait for that one to finish, and the other one so on. So one every 120 degrees, for example, that sort of thing. That will be decided by the pulse width modulator controller, and that's what's generating all these signals. Okay. The basic operation is this MOSFET turns on first, and it provides current into this inductor. But the inductor, being what an inductor is, it tries to resist the flow of current. It magnetizes, and while it's magnetizing, the 12 volts coming in doesn't appear at the output. If we switch this MOSFET off quick enough, we'll just get a lower voltage here. So effectively we switch it off before the full 12 volts can appear here. What then happens is we switch this one or these on, and that discharges the inductor. The inductor, when I say discharges, I mean demagnetized, and the collapsing magnetic field charges the capacitor. So it's the stored energy in the inductor when this one is switched on that powers the load and charges these capacitors when this one is switched off and this one is switched on. Okay. We effectively have 2 current paths, and they are alternate. So the first half of the sequence, the current is flowing that way, and then in the second half of the sequence, the current is flowing this way. Okay. So that's what the VRM does, and by regulating the amount of time this one is switched on to the amount of time that this one is switched on, you can change the output voltage. You can set the voltage to be whatever you want it to be. The problem when we have a short circuit here is it's difficult to find out where it is. And the reason being, the 12 volt supply goes to each set of MOSFETs, okay? Your 12 volts are all connected together here. It goes to all of the high side MOSFETs. And the low side MOSFETs are all connected together here. So ground is ground is ground. This is all the same place. So they're all connected together there. And then to make things really complicated, the outputs from all these coils are also connected together, CPU. This is all one point. And those coils to your multimeter will read like 0 ohms. So this makes it very difficult to figure out where the short actually is. On our board, we know something. We know that we don't have a short from the 12 volts to ground. That doesn't read short. That tells us that all these high side MOSFETs are okay. There's no short from here. The short is from here. Here we see it from here. We see it from here. We see it from here. All these points here are reading short. 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 And they're reading short to ground. And the problem is when you're measuring from here, it could be one of these that's short or both. Or it could be that you're reading with your meter via this inductor onto this rail, back via this inductor, and the short is actually there. Or, for example, again, you read a short here via this inductor, which reads 0 ohms basically, and this inductor, the short could be there. It's not possible to tell with a multimeter where this short is. Also, the short might not be in one of these MOSFETs. Remember, there are many, many capacitors connected on this CPU supply rail, this. It has many, many capacitors, and any of those could be short. And again, from here, we would just read the multimeter via the coil, via this rail to whichever capacitor is shorted, and we see a short. Yeah? And these are very thick tracks or power planes on the motherboard. They have practically no resistance, so once again, the same short will appear everywhere, even if it's one capacitor somewhere. And lastly, as I mentioned, this goes to your CPU. And the CPU itself could be short to ground. We know that isn't the case because we've removed it and the problem is still there. And this will go to at least one other place. And this is the PCH or North Bridge. Because that communicates with the CPU, it has to have a supply rail on the same voltage. And the PCH also connects to ground. And that could also have a short in it, so it could be in there. And lastly, we could actually have a defective motherboard with a short between the layers internally, so the short is in the motherboard itself. So you can see there's many, many places the short could be. And that makes it difficult to find, but it doesn't make it impossible. There are ways we can do that. So let's have a look if we can pin down where this is on our faulty board. So this is our 12 volts coming in, 2 pins are ground, 2 pins are 12 volt. And we know that this connects to the high side MOSFETs, the drains of the high side. Those are reading short, those are probably the ground pins. Yeah, and these are just climbing up in value as the capacitor's charged. So that's your 12 volts coming in on those two, and there is no short from there to ground. Now that we know will go to the drains of the high side MOSFET, so let's find them. We have 2 coils here, 2 capacitors. These are the low voltage capacitors. Okay, 4 volt, says on them 4 volt, 560 microfarads. So this is the low voltage rail, the V core. Now we know the 12 volts will go to the high side MOSFETs, and we see 1, 2, 3, 4, 5, 6 MOSFETs here. And then we see 1, 2, 3, 4, 5, 6 there, but they're like arranged differently. This is only one phase. So what I can see straight away is these 3 phases are not all wired the same. But I'm sure they're all supplying the same voltage rail. We can prove this anyway, so if we go from the 12 volts in, that'll go to the high side. I see 1 here, and then 2, and then 1 and 2. I think, but we'll figure it out. This is probably yeah, high side of one of them. Is there one up here? No, I'll bet it's that one. Yeah, that's the other one. So those are your two high side MOSFETs, drain, and then the source of these will go to the drain of the low sides. Yeah, there. And then the source of these two will go to ground. Okay, and the same with the other phase, this one. The source of this high side MOSFET will go to the drain of the other two. Yeah, and then the source of those two will connect together and go to ground. Back to front to each other. Okay, ground. And then we have this other phase here. So this one, again, from the 12 volts. Well, that goes to there, there. But not here. So we have 4 high side MOSFETs here, it looks. The sources will all connect together, I think. Yeah. Get good connection noise. Yeah. Yeah, and that'll go to the drains of these two. Let's have a look. Yes. Yes. And then the source of these will go to ground. Ground. Okay. So this has 4 high sides and 2 low sides. These have 1 high side and 2 low sides each phase. The way this works, this is a bit of a guess, but I suspect it is, that this phase with more MOSFETs is like the primary phase, the main one. So this one comes on when you power the board up. And these two effectively get switched on if this requires more power. That's my guess, which is why this one is the higher. Powered by the fact it's got more MOSFETs. So we know all the high sides connect together. Drains, drain, drain, okay. And the short is from the source of any of these, okay, which is also the drain of these. So this point goes to your inductor, yeah, and this is where the short is to ground. And we'll see the same from these ones as well. Okay, they connected to the same point, and these are connected to the same point. So you'll see on my resistance meter, if I measure to ground, it doesn't matter which phase I read the V core resistance on, it's still a short, okay? So the multimeter will not tell me where the short is. Let's have a look to see how we can determine it. Well, the first thing you might want to try is a low resistance meter, a milliohm meter. Let's see if that will tell us where the short is. Okay, I'm going to turn the board over, and we can see that the inductors, one is here, and the other one is there, okay? And you can see that this end of the inductor, there, and there, all connect together, okay? And this is your V core, this large plane here. The other end, well, one is there. You can see that track is separate from the other one. So this is the connection from the high and low side MOSFETs on one phase. This is another phase, and this is the third phase. What I'd like to see is if I can figure out which side of the inductor the short is on. So the way to do this, I'll connect my meter to ground. We'll go on this phase. While the resistance is higher than that, let me just go up a range. It's zeroed. So from here. And that's reading 1.7 ohms, okay? This phase is reading basically the same. This phase is reading basically the same. Okay, and the other side is reading basically the same. So unfortunately we can't determine with this meter where the short is, even to which side of the inductors has the short to ground. Okay, so that's not going to help us. A better way, and this will tell us where the short is, by the way, is to use an ESR meter. So with the ESR meter, we can measure the resistance, or rather the reactance, of an inductor. So these are the same sort of inductors that we'd find on motherboards and the VRMs. This one has more turns than this one, so this is a higher inductance to this one. And although an ESR meter is primarily designed to test capacitors, it will also test and measure inductors. The ESR meter sends a 100 kilohertz signal through the component you're testing, if it is a proper ESR meter. If you've got one of these little component testers that test capacitors and also tells you the ESR, that won't do this. It's not a real ESR meter. Okay, so I can show you now. If I take my ESR meter and I connect it to this inductor, it reads 0.788. So look, it has a reading. Okay, it's not a short like it is even to my low ohms meter. Here's another one. Okay, 0.19, 0.189. So I can use this to measure the effective resistance of the coils. How's that going to help us? Well, it's going to help us because there are also capacitors to ground on our circuit. So if I take a capacitor and I connect this to the ESR meter, this reads very low, 0.04, 0.05. Okay, let me explain how this is going to help us and then we'll look for our short. We know then that V core, this end of all these three inductors, are connected together. Okay, and they're also connected to ground via lots of capacitors. So to our ESR meter, this end of the inductor is coupled to ground via the capacitors. The resistance from here to ground is basically zero. It's the ESR of the capacitors. The other end of the inductor goes to the two MOSFETs, the junction or pairs of MOSFETs. In our case, one has 4 up here and 2 down there. Okay, this point is effectively open circuit to the 100 kilohertz signal because this has an extremely low voltage, the ESR meter, and these MOSFETs are turned off, and these are turned off. They're all turned off, so they're effectively not there. So this end of the coil to ground is open. Okay, this end via the capacitor is connected to ground as far as the ESR meter is concerned. So if I measure directly across each coil with my ESR meter from there to there, okay, I take my ESR meter and I measure. If the circuit is okay, like I've drawn here, what we will read is the resistance of the coil at 100 kilohertz. What happens if one of the MOSFETs is short? And this applies to high side or low side, okay? If this low side MOSFET is short, this point is connected to ground via the short, okay? This end of the coil is connected to ground effectively at 100 kilohertz by the capacitors. So the two ends of the coil are effectively shorted to each other, not DC, but at 100 kilohertz. So if that is short from there to there, I will read 0 or very close to 0. What happens if a high side MOSFET is short? I know ours aren't, the resistance meters told us that, but if we have a short from 12 volts to here, the same problem applies. But imagine this MOSFET is short and that one is open. Okay, that one's good. This is short. What happens now? Well, we know this end of the coil is connected effectively to ground at 100 kilohertz, and this one via the shorted MOSFET to the 12 volt rail. And what's on the 12 volt rail? Lots of capacitors to ground. So this end of the coil is also effectively connected to ground via these capacitors. So once again, I will see a short across the coil, and this will tell us where the short is. If the short is somewhere in the MOSFETs. If the short is on this side, yeah, not only connecting to ground via these capacitors, but also shorted to ground as well, DC, then I will see the resistance of the coils will all be the same. Okay, let's see what we've got. I'll put this here because the leads are very short. Okay, and let's have a look. So we're going to measure across this coil. Okay. And we see 0.35 ohms. That's what you'd expect to see on a good phase, just the same as I showed you with those other inductors out of circuit. This one, 0.37, so it's very close. It's very close, okay? The last one, if this one reads the same as well, then the short is on the V-core side. If it reads low, the short is on the MOSFETs on this one. Let's have a look. 0.019. So guys, we know now that the short is on this phase and it's on the MOSFET side, and because we don't have a short to 12 volts but we do have a short to ground, we know it's a low side MOSFET. And there are only two of them. 1, 2. Okay? It can't be a capacitor because there are no capacitors from these coils on this side to ground. This thing is pulsing at extremely high frequency. The last thing you want on here is capacitance to ground, okay? So it can't be a capacitor. It's got to be one of the low side MOSFETs. And we actually know it's the one with the 4 and the 2. Right. There's our fault. Could be one or both of these. But while we're here, let's just try another method anyway. So I'm going to show you another way to do this with your bench power supply and using a millivolt meter. And then let's try the thermal camera as well. To do this with a millivolt meter, I'm going to inject current here. Remember, the 12 isn't shorted to ground. I'm going to inject current directly to the V-core. I'll set my power supply to 1 volt. So even if the short disappeared, the voltage can't go above that. It won't damage, for example, the PCH. I'm going to put current in here. Now, we know already, because we can see that we have short on the low side MOSFETs on one of our phases. But we should be able to detect that by measuring the voltage in millivolts on the most sensitive range on our multimeter across the coil, because the current will flow through one of the coils, the one with the short circuit low side MOSFETs. So we should see a reading on one of them, the same one that the ESR meter told us. And on the other ones, well, if these MOSFETs are okay, no current can flow that way. So we'll basically see 0. We might see a tiny bit of current, and the reason being the pulse width modulator control here, PWM, also has a signal called phase, which goes from the chip and it connects also to here, okay, to the actual junction. So we might actually see some current going that way, but it would be very low. Let's have a look and see if we can see more current giving a higher voltage drop on the one where we know the shortest. To do this, I have my bench power supply set to 1 volt, maximum current. I've clipped the negative lead to ground. And I'm going to attach the voltage supply to the V-core, okay, which is any of these. Let's just clip it on. And we have about half an amp. That's as much as I can get in there. I don't want to increase the voltage anymore because that's connecting to the PCH. So that's what I have. Can we see where that current is going by measuring the voltage in millivolts across our capacitors? So I'm on millivolts. This will read down to 0.001 millivolts. Okay, that's about a microvolt. And now we're going to measure across the coil to see if we see any voltage drop. This should tell us if any current is flowing through here. So that's reading 0. So there's either no current or it's so low we can't see a voltage drop. This one, 0. Can we see across this? Yes, 0.365. So we know all the current is flowing through that one. Again, this is the one with the 4+2 MOSFETs. We know the ESR meter said this is where the short is. So that's telling us the same. Now, will the thermal camera tell us? Okay, so here is our thermal camera. We can see the board with all the MOSFETs. Okay, I'm going to inject some current now. Yeah, we can see on the meter we're injecting current. Can we see anything getting warm? Well, we know the short is actually over here. That's the low side MOSFETs where the short is. High side. And the fact is we don't see anything. Okay. The reason we don't see anything is because the resistance of the short is practically 0. Therefore, the voltage drop across the short is also practically 0. Okay, so the wattage, which is voltage drop times current, because voltage drop is basically 0, the wattage is basically 0, therefore nothing can warm up. Okay, so the thermal camera won't help us, but we have two good methods that did. All we really need to do now is remove these MOSFETs and then let's see if the short has actually gone. So, ground, okay, short has gone. Okay, you can see it everywhere. Yeah, it's just charging capacitors up, it's gone to open now. So that was the short. I have the two MOSFETs. Well, that one reads okay, this one. Short. Yeah, there you are, guys. And that's how you find short circuits and VRMs. We used 5 methods there, okay? Multimeter didn't work. We could see the short, but we could see it everywhere. The milliohm micro meter didn't work. We could read the resistance of the short, but it was the same everywhere. ESR meter, that is my favorite. It worked perfectly. And that also will find high side shorted MOSFETs as well. Injecting current and using the thermal camera didn't help us at all. Injecting current and measuring the voltage drop across each inductor, that told us the fault and confirmed what the ESR meter told us. So that's the way to do it, guys. A lot of you have an ESR meter. That's an excellent use for it, as well as providing bad capacitors. The rest of you, I'm sure, have a bench power supply and a multimeter. As long as your multimeter will read millivolts, then it's ideal for this job. Okay, hope you enjoyed that. Comments below. You may have a few other suggestions. If you use a different method and you prefer it to the ones that I use, or you think it's better in some way, let us know and let us know why it's better. Otherwise, if you just want to say hi because you enjoyed that, I'd love to hear from you guys. Okay, I'll see you all soon on another Learning Electronics Repair video. Ciao for now, guys.